Oh shit. Here we go again.
Okay, I want to make sure this is actually recording. Looks like it is. Make sure. Yeah, okay, good deal. We are recording. Thank God. Okay, so let's do some background on this problem. This symbol right here means average normal stress. I did actually record a better audio for this actual video, which I may post later, but my internet's dead at my house, so we're just gonna have to deal with this. All right, N is the internal resultant normal stress. All right. And then A would be your cross sectional area. Okay, good deal. That's our background that we're going to need for this problem. I would commit some of this stuff to memory. This is very important to know, especially as we get into some of these other problems. All of these things are connected as the average normal stress equals the internal resultant normal force over the cross sectional area. We're going to need that to solve this problem right here. The units are going to be in pascals or psi. Uh, PSI is a pound over inches squared, and then Pascal would be newtons over meters squared. I hope y'all can't hear the stream I'm watching right now. I'm watching a Ludwig stream. Yeah. All right. So some stuff you may see is like 1 times 10 to the third power Pascal would equal kilopascals technically. Well, not technically, it would. 1 times 10 to the sixth would equal that Pascal. I need to figure out what that actually says. All right. 1 times 10 to the ninth Pascal would equal 1 gigapascal. There is actually a mechanism for learning that. It's like, uh, fuck, it mentions a king or something. I don't know. Okay, let's read this problem statement out. The bar has a constant width of 45 millimeters, a thickness of 13 millimeters. Determine the max average normal stress in the bar when it is subjected to the loading shown. Okay, so we got our A, we got our B, and we got our C. And obviously, max average normal stress is what we're solving for this symbol right here, which means average normal stress. Okay, I believe we're probably going to define some forces. Sorry for this video right here. I did record this, a better quality version of this, but like I said, my internet's out, and I do want to get this video out tonight for y'all. Um, so we're defining our stuff right here. So we got 50 kilonewtons all the way on the left. We got our 12 kilonewtons on the top and bottom. And then at C, we have our 7 kilonewtons acting at the top and bottom as well. And then at the very end, we have our 30 kilonewtons. This box right here is for later. It's like, for finding area, you got to do your base time, your width. Most people know this. You should know this if you're here, to be honest with you. Okay, let's see what's next. Okay, so this is where we're going to make our cuts. Cut 1, cut 2, and cut 3. So yes, we're between A and B we make a cut. Between B and C we make a cut, and between C and the very end we'll make another cut as well. And we're going to do these separately. And I believe we're going to be acting as if this is tension, so it would be a positive. It's assumed to be positive. If it was compression, it would be assumed to be negative. All right, so we need to solve for the N max, which is going to be our average normal stress, and the area is constant. So when we solve our area, it's going to be constant for every one of these. All right, cut 1. Okay, let's see what we did here. So we're just defining our cuts right here. Got our 15 kilonewtons right there. We're gonna have our NAB right there, as well as on the other side as well. And we're acting like this is tension, so it's assumed positive for both. NAB as well on that side. Now, which one of these are we going to choose? Now we can define we're defining our 12 kilonewtons on the top and the bottom, and then our 7 kilonewtons as well on the top and the bottom, and then we'll put our 30 kilonewtons on the very end. But which side are we going to really want to use? Probably going to use the left side, to be honest with you. It's what I would do. We're going to use that probably because just in general, it's just a lot easier to use it. When we solve for NAB, it's going to be really simple. So let's solve for the fx direction. All right, we're not solving for Fy because there's just there's no forces in the y direction, so we're not taking them. You could take it if you wanted to, but I mean, there's no point. It's just going to equal 0. So okay, let's go ahead and take it. So it would be minus 15 kilonewtons plus NAB. Positive times a positive because it's positive. It would always be a plus sign right there if we assume it's tension, but if we assume it's compression, it would be a negative. There's going to be another problem. We're going to figure this out a little bit better. And this is where we chose that one, NAB equals 15 kilonewtons. Cut 2. Okay, we're only drawing the left side on this one. Let's see what we drew out, actually. We had our 12 kilonewtons on the top. We also have our 12 kilonewtons on the bottom as well. Our 15 kilonewtons on the very end on the left. And then we have our NBC right there. We're going to assume it's positive because of the tension. There is actually a problem that I can actually explain the whole tension and compression thing a lot better because it's really simple. Like it really is just like what you would multiply it by, assuming if it was compression, it would be like multiplied by a negative. Even if it was going in the positive direction, it would be like negative times a positive. But if it was tension, if it was negative, it would be like a negative times a positive or a positive times a negative. Like I said, it's an easier problem. Okay, so we summed it up. We had two negative 12 newtons. I want to make sure we know that it's not the same. And so our NBC would be equal 29 kilonewtons. And that's one of the things we're going to need to use to solve for. Um, so what we're doing next. Let's go to cut 3. All right, I drew the left and the right one because for this one we're actually not using the left. Obviously, because it's just a little bit easier. The NCD, we're going to be doing basically the same thing. When we solve for stuff in the x direction, the NCD is just going to equal somewhere around the 30 kilonewtons. All right, so let's take our summation of forces in the x direction equals 0. All right, we go in there. It'd be negative the NCD because it's going negative in the direction. So that's where it is. Okay, so we assume that that's positive. So we just need to assume there's a positive force. So it'd be a positive times a negative. Great. That's what we need to explain. Because we're assuming it's tension. It's a tension thing. We could solve it as compression. It really wouldn't matter in the long run. You're going to be, it all equals out the same way because of the way we do our negatives. It's just, you're making an assumption, basically, in a lot of ways. Yeah. Okay. So NCD plus the 30 kilonewtons equals NCD equals 30 kilonewtons. Good deal. So that's cut 3. I didn't draw it at the top all the way. I guess I got a little excited and forgot to draw the cut 3 all the way. Um, oh well. Okay, because I'm recording this video, and I'm kind of just doing a voiceover. What are we looking for? We got to compare NBC, NCD, and NAB. That's actually what we're about to do. When we look, we see that NCD is actually our biggest at cut 3, at 30 kilonewtons. And because NCD is bigger than NBC and then NAB, we need to take our average normal stress maximum at NCD because it's the max stress in the segment CD. Or the max stress is going to be in the segment CD. All right, let's calculate max at NCD. Okay, so we know that the average normal stress CD will equal the normal maximum at CD, or the normal force, we're just calling it in max, over the area. Okay, so it'll be 30 times 10 to the third newtons. We're converting kilonewtons into newtons for this. And then 13 times 10 to the negative third meters, because we're converting it the millimeters to meters, as well as the 45 times 10 to the negative third meters, because as well we are also converting that into from millimeters to meters. And when that equals, we're gonna get probably. I was probably solving the answer out with my calculator right here. So, all right, now we're gonna solve it. I cut that section out because I done the problem wrong with the calculator. Um, the actual answer is gonna be. I know it's gonna be 10. It's gonna be something times 10 to the 6, and we're gonna convert it from those pascals into something a little different. It's still going to be in pascals, but it's going to be, so it'll be 51 um, 0.3 times 10 to the negative 6, or, well, not 10 to the negative 6, 10 to the 6 pascals, or 51.3, whatever pascal that is. And that would be our final answer. All right, guys, on to the next one. Good deal.